Hi guys, Sajjad Hussain again. Today I came with a new video. This is related to the beam design, steel beam design, and this you can say that this video is in continuation of my previous video where I design a beam, and I take the solved example. Now this is another example. Here you can see that the span is 35 feet and it is loaded with dead load of 0.45 kip per running foot and a live load of 0.75 kip per running foot. This beam was designed and it was found as W8 by 50, which is going to qualify for these loading conditions. The allowable moment, the applied moment was 184 kip feet. Now here the condition is that this beam is braced at the ends and thread points rather than continuously braced. The previous example was a continuously braced beam, but now this is not a continuously braced beam. It is braced at middle thread points. And LB, as per the definition of code, that means unbraced length is 35 feet divided by 3, so 11.7 feet. And by inspection from the table 3-1 of the manual, CB comes out to be 1.01. Okay, and at the end the total moment comes out to be the resistive moment comes out to be around 200 kip feet, which is of course more than 184 kip, which is the applied load. So that means still this beam is safe. Now let us try to solve this problem. This is the previous input data file which I uploaded again. The total length of this beam is 35 feet or 420 inch. Okay, fine. And now same as before, but here in design phase and design parameters, what we have to do, we have to revise this UNT value. That means unsupported length for the top flange. 420 inch divided by 3 comes out to be 140 inch. I added the command here, unsupported length of top flange for calculation of bending capacity is 140 inch. And for the deflection check, same thing, and same unsupported length here is 140 inch. Let us close this one, and in this case my CB value I have taken as 1, which is default, so I did not change now. CB is 1, I have not changed, same default value. Let us run the analysis. No error, no warnings, no notes. Let's see the output data file. So here 1.001, it fails. But for deflection case it passes. A slight difference is 1%. That's okay, we can ignore. Or let us change this value of CB. It's 1.01. Let us revise, close, and here again edit 1.01, modify, close. Let's see what the result is now. Save. See the output file. Now it passes 0.997 and here is 0.930. That means the applied moment and the resistive capacity of the beam is very close, so this is okay. And if we compare our results with this, so again the values are very close, 201 and 184. 184 is the applied. Let us check. We'll go to post processing. Only load case number 3 is needed. So for load case number 3, let's see the bending moment. Bending moment is 184. We can show graphically. Bending moment maximum 184 kFit. If we divide 184 by 0.93, 184 is divided by 0.93, it comes out to be 197 or 198, which is very close to 201. So that means our result is exactly same as the calculated values. So what we can conclude over here, that if we take the CB value of 1.01 as from the manual and we define our UNT parameter, which is the unsupported length for the top flange, as L by 3, so still this beam is qualifying, this beam passes, and here is the result is okay. That means STAAD is calculating absolutely the same value. The second part of it is very interesting. The second part here, it shows that the value of CB as per the formula of equation F1-1, which is from the manual. Let's see on the manual the formula. This is the steel construction manual, of course 13 edition. I can go directly to the page where value of CB is given. The value of CB, it is lateral torsional buckling modification factor, and this value is defined like this. All these parameters are defined over here. You can check. Another aspect here is when CB is calculated, here there are two values of CB calculated. Number one, for the lateral torsional buckling limit state, the non-uniform moment modification factor can be calculated using a specification formula, this one. Now here what they have done, for the center segment of the beam, the required moments for equation this can be calculated as a percentage of the maximum mid-span moment, M max. We know that for M max our value is 184. Keep fit. So if this is 1, so for the middle third section on the left hand side, MA will be 0.972 and MB will be equals to 1, and MC again on the right hand side it will be 0.972. And for doubly symmetrical section, this RM is equals to 1. So when we apply all these values, CB comes out to be 1.01. This value is correct for the middle section, but for the end spans, for the end span beam segment, the required moment for equation this can be calculated as a percentage of the maximum. Now maximum will be 0.89 and MA will be 0.36, MB will be is equals to 0.556 and MC is equals to 0.75. I'm not going into details of these moment calculation. One can do it very easily. And then the CB comes out to be 1.46. This is for the end spans. Thus, for the center span, with the higher required strength and lower CB value, the governing factor will be this one. Now LP is 5.83 feet and LR is 17.0 feet. Now LP and LR, these are already specified in table 3.2 of this specification. We can see in table 3.2 over here, this is table 3.2 and our beam is 18 by 50, W18 by 50. So this is the line where we should read. LP is 5.83 and LR is 17. What exactly is LP and LR and what is the concept? Let's go and check. LP corresponds to a length for plastic moment and LR corresponds to the elastic moment with 0.7 of Fy into Sx. So if our length is in between, so that means this plastic hinge will not be formed and it will be within the elastic range. So going back to the problem, and we will see the conclusion. What is concluded over here? That the more conservative formula for LR given in the user, this can yield very conservative results. For a compact section, of course W8 by 50 is a compact section, and unbraced length LB, which is lying in between LP and LR. LP is 5.83 and LR is 17. The lesser of the either of the flexure yielding state or the inelastic torsional lateral torsional buckling limit state controls the nominal strength. So here we calculate the nominal strength, and as per this the nominal strength comes out to be 203 kV, and we calculated that for this case our nominal strength comes out to be around 200 if we take the value of Cp is equals to 1.01. So what we can conclude that we can use STAAD to design a steel beam, and we have checked its parameters for lateral supported conditions, and we found that the results are absolutely perfect and they are matching with the calculated values. So this gives us a confidence that STAAD give us very accurate results. Thank you for watching. Please do not forget to subscribe my channel, and please like this channel if it satisfies you. Thank you very much.